they can easily block them, right? The content moderator can block them. So that may be useful for that point of view. And in other sense, this is also useful for to understand influential users, right? If say given a tweet, if user U has posted it versus user V has posted it, who would going to be the influential user in order to propagate this particular tweet, right? And this information diffusion is not only studied for social media content, is also studied in other contexts. For example, say research, right? Scientific research. When somebody cites another paper, so say I'm writing a paper, the cited paper, okay? So in that context, you can also track whether a particular topic, whether a particular research area, particular research theme, how this research theme has propagated from one researcher to another researcher, from one paper to another paper, and you can also predict which topic is going to be viral, you know, in next couple of years. There are plenty of research on that, but in this particular tutorial, we'll mostly focus on research on two aspects. One is social media information diffusion related to hate speech and fake news, and other is information diffusion in epidemiology, right? Disease spread, for example, say coronavirus spread, or say, you know, HIV virus spread, and so on and so forth. Swine flu, you know, Spanish flu spread on offline network, on offline person-to-person interaction, and so on. So as I was mentioning, this information diffusion has been studied in different areas, sociological areas, you know, epidemiology, and of course ethnography, to understand the culture and background of different societies in different parts of the world. So for those who do not have much idea about the network, so here, by the word network, I mean to say graph, right? Not the computer network. It's a graph where nodes are users, and links are different types of relations between users. Links can be friendship relations, links can be follower-follow relations, or links can be, you know, retweet. If someone retweets another some other tweet, that you can think of links between one user to another user, and so on and so forth. So so we study information diffusion in social networks, say Facebook friendship network. We also study information diffusion in World Wide Web network, where nodes are web pages, and links are hyperlinks from one web page to another web page. You can also study information diffusion in World Wide Web network. It's a very famous network. You can also study information diffusion in a normal information network, for example, citation network, right? Or paper-to-paper citation network, or say author-to-author collaboration network, right? And or say possibly a computer network, say where nodes are hubs or computer machines, right? Routers, computer machines, and links can be drawn if one computer machine, if one hub or say one router sends a package to another router, you can think of a link between two routers, and so on. It has also been studied in information diffusion, has also been studied in other contexts. For example, transportation network, right? Say railway network or airlines network, protein interaction networks in biology, or again, right? These are heavily studied by biologists and physicists, including Barabasi and other researchers working in this particular field. And you can also think of Internet of Things as a network. So in fact, you can create networks from any data set, depending upon the task that you want to solve. Okay. So now, forces influencing diffusion, right? What are the aspects? What are the properties or characteristics which influence information diffusion, right? So one is infectiousness, right? How likely to spread a particular thing rapidly, right? How interesting is the piece of information? If the piece of information is not interesting, then of course, you know, it's less likely that it will be spread. It will spread rapidly, right? Resistance. When we talk about spread, at the same time we talk about how how a particular node is resilient or a particular node is resistant against a particular information, right? For example, say I am resistant to coronavirus spread. I have already taken a vaccine, right? So I will not act as a carrier for COVID-19 virus, right? So I am resistant. Similarly, say for example, I am a supporter of BJP. So if I get any news related to anti-BJP, I will not spread it because I'm already resistant to that ideology or that topic, right? Network topology plays an important role. So the idea is that if a part of the network is very dense, right, it is very highly likely that the information will spread rapidly. So in that context, research, there are studies which basically say that, when you start spreading information, what are the nodes that you should attack first? So these are the set of nodes which you should attack first, and because these are the nodes which are more influential, right? For example, say if you want to now promote, say you are devising a new coronavirus vaccine, right? You want to promote your vaccine, right? Now what you do, you possibly target some of the influential persons on social media who are very active, right? So possibly say you want to convince say Shah Rukh Khan, or you want to convince Amitabh Bachchan to promote your vaccine, right? But at the same time, you know that convincing them is very difficult because they would charge a lot in terms of money, right? And you do not have that possibly that amount of money to invest for this promotion. So in that context, the problem is, given a budget, right, or given you can quantify budget in different ways. Given a budget, what would be the set of nodes which you target in order to maximize the spread as much as possible? Okay, this is called initiator identification or seed set identification in social network analysis terminology, right? Strategy. So again, this also comes under the strategy. How do you promote your event? How do you promote your activity? How do you promote your fake tweet? How do you promote your hate speech, right? So that the spread the spread maximizes within a certain point, within a certain duration, right? So some of the common terminologies that we use in this tutorial, remaining part of the tutorial, is, as I mentioned, seed nodes, right? Seed nodes or senders. These are the initiators who who are responsible for spreading the hate speech, or hate speech or fake news, whatever. Infected or activated nodes. So these are the nodes which are infected over time, right? So when we talk about infected nodes in case of social network, we basically say that if a user retweets a particular tweet, that means that user has already been infected by that tweet. Okay. Susceptible nodes, those nodes which are exposed to some information but have not infected with it, right? For example, say I see that most of my friends are spreading fake news. I have already exposed to that. I've already seen that they are spreading, but I have not spread so far, right? So I am susceptible. I can spread the news at any time, but still I've not shared that news, right? That's why I'm susceptible in that sense. Information cascade, a sequence of nodes in order when they are infected in the diffusion process, as I was mentioning, right? So given a particular node from where information starts spreading, what would be the sequence of nodes through which that information will spread over time, right? This is called information cascade. Social influence. This is a social phenomenon where actions of a user can induce his connections to behave in a similar way. For example, say I have 100 friends, and I've already seen that 70 out of 100 friends have already posted a fake news. So I am kind of forced to post that to share or retweet that fake news, right? It's called social influence. The influence coming from my neighbors, from my friends. Hard behavior. This hard behavior is saying that, irrespective of whether what is my, I mean, irrespective of what is my private ideology, my internal ideology, right? I may act similarly as what my group does. For example, say again, let's say I have 100 friends, and most of my friends are BJP supporters, but I am a Congress supporter, right? I may act as a BJP supporter in order to pretend myself as a BJP supporter, so that I am safe, so that I will become safe. I will not, I will not be, I will not be uh, mm, uh, I will possibly start doing something which would which I mean, I will not do something which would possibly depress my friends, or possibly upset my friends. So I will not do something. So this is a group based behavior. This is not an individual behavior. So whatever my private information is, I will not use my private information, or private signal, private ideology to do the action, right? Action means sharing or retweeting. Close world behavior, we assume that the diffusion is dependent only on the closed world of social network. Say, for example, if I spread a tweet or retweet a tweet within Twitter, right? I am only influenced by the internal signals of Twitter, not any external signals. This closed world assumption is wrong, though. But in general, when we design any model, we assume that the world is closed, and the information, we are only getting information from the internal world, and the internal world is the social media itself, for which we want to design the model for information diffusion. Right? I hope the terminologies are clear. So now moving on to the basic models of information diffusion. Okay. So so let's skip this, because I've already mentioned the task, the objective of all this predictive model. The objective of the predictive model is to identify or to find the set of nodes which are going to be infected by a certain information, right? So the basic model, the simple model, is called IC model, independent cascade model. Okay, the idea is very simple. Think of it as there is a network, right? Again, users and links, and there is a seed node or a sender node. Okay, and let's look at this example. So assume that this is the network, and V1 is the seed node or the sender node who starts the diffusion process, and these weights are associated with edges indicating certain probability. Okay, now how these probabilities are used, right? We'll discuss. So what this model does is that now, in order to decide whether V1's friend, V2 or V3, who will be infected by this information, right? What we do is that we toss a coin. When we are at V1, we toss a coin, right? For V2, for example, we want to check whether the information is moving from V1 to V2 or not. We toss a coin, and if the output is less than this weight, the probability, say for example the output is 0.4, right? And 0.4 is less than 0.5, it means that V2 will be affected. Right? Here again, you toss a coin for V3. Now these two events are independent. Okay, you toss a coin for V3, and you see that the output is 0.9, which is greater than 0.8. It means V3 will not be affected. Very simple model. Okay. Similarly, when you come at V2, you again toss a coin and see that the output is 0.1, which is less than 0.2. It means V4 will be affected. Okay, and so on and so forth. So it's a very simple model, and by this way you try to mimic the information diffusion on social media. IC model is one of the first models to model the information diffusion on social media, right? So now you possibly looked at one point here is that it is dependent on the activity at the source level, because at the source level, at the source node, you toss a coin. It is not dependent on the target node, right? So in order to address this problem, there were other kind of models which are called linear threshold model. Okay, in linear threshold model, what it does is that it is receiver centric. This is not as opposed to the earlier one, which was sender centric. This is receiver centric. What it does is that at particular time t, okay, you look at v is a receiver, right? Now you want to predict whether v will be affected or not at t plus 1, right? So at t, you look at v's neighbors. Okay, you look at v's neighbors, and you have some sort of combined some sort of aggregated belief of the neighbors on a certain topic. Okay, and v itself has a threshold called activation threshold. Okay, if the aggregated belief crosses the activation threshold, it means that v will be infected at t plus 1. Okay, this is a receiver centric model, and you do the same thing, and then you see whether this model mimics the real world behavior or not. Similarly, you also have game theoretic models where you define certain profit and loss, right? You think of it as a two-party game or a multi-party game, and if one user convinces another user there is a profit, right? There is a cost associated with that, and you play the game, and you see that at the end of equilibrium condition, what happens? What would be the number of infected users or number of susceptible users at that point, and then you measure it with respect to the ground truth, evaluate it with respect to the ground truth. Okay, these are very preliminary models which are proposed long time back. Okay, for general information diffusion task. We can take some questions if there is any. Okay, so let's move on. So the next set of slides will be on diffusion with respect to the epidemic model. Okay, you may have heard about this epidemic model called SIS model, SIR model, SIRS model, and so on. We'll discuss them very briefly here. So unlike IC model or linear threshold model, the one that we discussed, where we assume that there is an underlying network structure, users and nodes and links are their relations. Here, when we model any epidemic spread, there is no network structure as such, right? There is no network structure as such, because we do not know who is going to contact with other individuals in the society, right? So we do not have explicit network structure as such, right? So the first model which was proposed is called SI model. S stands for susceptible, I stands for infected. Okay, so these are the notations that we are going to use. N is the number of crowds, the number of populations, number of users, right? Total number of users. What is ST? ST is the number of susceptible users, susceptible individuals at time t. Okay, you remember the definition of susceptible? Susceptible users are those who are prone to that virus or that information, right? But those who have not been infected yet till t, right? And what is IT? IT is the number of infected individuals at time t or till time t. Okay, capital IT. And what is beta? Beta is the contact probability. So right, when beta equals to 1, everyone comes to contact with everyone, right? When beta is 0, there is no meet as such. Okay, so beta is a contact probability. Now we use these terminologies to model the spread. So in general, at any point in time, at any point t, ST plus IT would be N, because ST is the susceptible users and IT would be the IT is the number of infected users. So in total, the sum of ST and UT, sum of ST and IT would be N, right? So now let's try to understand this model, right? So at every time stamp, at every time t, an infected individual will meet beta times n people, because beta is the contact probability and n is the total number of people, total number of individuals. So at any time t, beta times t number of individuals will be contacted by one infected person, right? And how many of them will be infected? There are S number of susceptible users, right? So beta times S number of users, susceptible users, will be infected at a particular time t due to one individual infected user, right? So if there are I such infected users at time t, so total number of susceptible users who are going to be infected would be beta times I times S. We have beta times S for one infected user and times I. So beta time I times S. So this is the total number of infected users at a particular time due to I number of infected users. Okay. Now DSDT. What is DSDT? DSDT is the rate of change of susceptible users. Right. This is DSDT. So what is DSDT? DSDT says that what would be the number of users who will move from susceptible stage to infected stage, right? And we have already seen this is beta time I time S. Now why negative? It is negative because the number of susceptible user decreases. This is negative. Similarly, the same quantity will contribute to the infected case. So DIDT is the rate of change of infected users, right? And the same quantity will be there because the susceptible users will move to infected users. The same quantity, but the symbol would be different. This is minus, this is plus, because S will decrease and I will increase. This is rate of change of infected user, right? And this is rate of change of susceptible user. So now we can replace S by n minus I, because we already seen that S plus I equals to n, right? So we replace S by n minus I. Now when we take now this is the derivative. When you integrate it with respect to t, we get the values of it, and this would be the values of it when you take the integration here over t. Okay, so this is the infected. This is the number of infected individuals till time t. Okay, so now this is the simulation output, right? What it is doing here is that what it is showing here is how we can minimize this grid. So x-axis indicates the so x-axis indicates the timestamp, and y-axis indicates the population. Okay, so as the time increases, as you see, so this is a simulation output. As the time increases, number of susceptible. So this solid line indicates the number of infected users. The broken line indicates the number of susceptible users. So as you see, number of infected users is increasing, and number of susceptible users is decreasing, which is very obvious. And when this model was invented, the simulation result was compared with the real world result. This is the real world result of AIDS virus spread with time. So x-axis is the year, y-axis is the number of new user case. And as you see, this curve, this is the number of infected users. This curve follows similarly as the model predicts, right? So essentially, it indicates that this HIV virus spread might be mimicked, might be modeled by this SI model. Okay. So now coming to the second model, which is called SIR model. So here a new state is introduced. It's called recovery state. S susceptible, I infected, and R stand for recovery state. Okay, here also we have this beta parameter, which which indicates the rate of change from S to I, susceptible to infected, right? And there's another parameter gamma, which controls the change from I to R. Okay, now let's look at these equations again. So DSDT we have already discussed earlier, right? This is the rate of change of susceptible user, and this is minus because S will decrease. What is this? This is rate of change of infected user. This quantity will be same. Now some users are moving from infected to recovery, right? So therefore, and what's the ratio? What's the number? The number is gamma times I, because I is the infected, I is the number of infected users, and gamma is the probability that an infected user will recover, right? So this quantity will be reduced. This quantity will be deducted from the actual value, right? So this is the rate of change of infected users, and of course similarly this quantity will play the rate of change of recovery user, right? So these are three equations, and similarly here also you take the you take the integration, and you will get the the number of susceptible users, infected users, and recovery users at a particular time. Okay, so this is again the simulation result. X-axis indicates the timestamp, y-axis indicates the population, right? As you see, number of susceptible users reduces over time, number of recovery users increases over time, and number of infected users increases, right, at a particular time, up till a particular time, and then it decreases. Okay, and this simulation result is obtained by setting these parameters, right? Beta is set to 0.01 and gamma is set to 0.1, right? And most of the, if you see most of the epidemic spreading, right, they actually follow this SIR model. So there is another model called SIS. Okay, susceptible, infected, then susceptible. There is no state called recovery, right? So they would get infected, they would again move back to the susceptible stage, right? So here also again you see these two parameters are used beta and gamma, but this time gamma is used as a transition probability from I to S, right? And the equation is more or less same. So if you understood the previous equations, you also be able to understand this equation, right? So and it's very evident that S will decrease and I will also increase. It's called SIS model. There is another model called SIRS, right? It is saying that from infected you might be recovered, but there is no guarantee that you will not be infected again. So you will again you will again be infected. For example, say if this COVID-19 vaccine is not that effective, or if the COVID-19 vaccine is say effective for 6 months, so after 6 months you will again be infected, right? There is high chance that you will be infected. So from recovery state you can move to the susceptible state, right? So as you see, there is another parameter lambda. So beta indicates the transition from S to I to R gamma, and R to S again this lambda. Okay, SIRS model plays and is basically stands at the middle of SIR and SIS model. Okay, this kind of models may be useful when you see that, you know, for example, in case of this coronavirus, right? I'm possibly sure that this kind of model would be more useful than the models like SIR or SIS or simple SI model. Okay, so in case of infodemic, or in case of information diffusion in social media platform, people adopted these epidemic models, SIR, SIS models, right, in different ways. For example, this ACIR model. Here they introduce another state called exposed, susceptible, exposed, infected, and recovery. Now, what is this exposed? Exposed means, so here the susceptible state means you know that something is happening, right? But your friends are not susceptible yet, right? Not exposed, not infected yet. In other words, you know that in some cases, say you know that some of your friends have already been infected by coronavirus, for example, right? But you may not, but you have not visited their places in last 2 weeks. So you know, you are not exposed to that. You are susceptible, but you are not exposed to that, right? In another case, people introduce another state called contacted. So ACIR model, same thing. In case of exposed, they used as a state called contacted. Here the meaning is that you possibly visited your neighbor's place, your friend's place, but you were still not been infected. You are not being reported as an infected person, right? So you are being contacted, but you are not infected yet. Okay. So depending upon the task in hand, these epidemic models have been adopted for information diffusion in general. Okay. Now coming to some of the recent works in hate speech diffusion. Give me 1 minute. If we have any query, I can take. Hello, sorry. So I hope I have 15-20 minutes, right?
Yes, Tanmoy.
Okay, great. So Delhi is extremely cold. I'm switching on my heater now. I'm terribly shaking. So that's the reason. Okay, so the first so the paper that we are going to discuss is a text-based diffusion model. It was recently published in 2019 website conference, and so here the idea is that so they tried to understand how hate speech diffuses over social media, and how the spread of hate speech is different from the spread of other type of text, right? So uh, so the post of hateful users diffuse significantly further. So these are their key takeaways. They spread significantly further, wider, deeper, and faster as compared to the non-hateful tweets, right? Post having attachment, right? For example, say a multimedia content or a meme, it is highly likely that they would spread first, and then it is also highly likely that this post will be viral, and hateful users are more proactive and cohesive in the sense that they are part of a dense community in a social network, right? And hateful users are more influential due to the significantly large volume of structural virality, average path length, etc., etc. Right? So let's look at the data set that they used. They used a data set from Gab. So some of you may be familiar with this platform called Gab. Unlike Twitter and Facebook, Gab doesn't have any restriction on the text, so people can write hateful tweet, fake news, whatever they want. There's no restriction. There is no content moderation as such. So they collected information from more than 20 million posts, more than 300k users from this platform. And the features that they used include network-based features like follow, user-level features like post, likes, dislikes, and they also manually annotated some of the tweets as head tweets, and they also collected the lexicons for this task. Okay, so head lexicons for this task. So then in their model, what they did is that they created this repost network. Now, what is this repost network? As you see here, right? So say for example, A has posted something and B has retweeted that post. So that you can create a link from B to A, right? And this number indicates number of such posts that number of such posts of A that have been retweeted by B or shared by B, right? So this is a repost network. And you also see that there's a self loop. The self loop indicates that people are sharing their own tweets again and again, right, in different ways. Now from this repost network, they created a belief network. The belief network is same as the repost network, with the difference that the direction of the link is the opposite here. So if B post, if B shares A's post, it means that there's a belief propagating from A to B, right? So you see here in this network, the H direction is just opposite, okay? And these numbers are again calculated in the same way. For example, say, this B, user B. So user B has posted, user B has shared 3 posts written by C and 9 posts written by A. So total 12 posts have been shared by B, right? So the belief coming from A to B is 9 by 12 and the belief coming from C to B is 3 by 12. Okay, in this way. So this is a kind of a belief network you can think of, right? Now then what they are doing now, they are doing the same kind of thing that we do in case of PageRank or any iterative algorithm in networks. What they're doing here is that at time I+1, look at B. Okay, so at time I+1, B's belief is updated by A's belief and C's belief with the weight corresponding to the edges, right? So right, and therefore the idea is that and you repeat this process again and again. Say at t equals to 1, t equals to 2, t equals to 3, you keep on doing this thing again and again until unless you see that the belief, or either the overall belief or the individual belief of users do not change drastically. So there is a threshold. If you see that the change in the belief of individuals between 2 consecutive timestamps is not drastic, or if the change is below a certain threshold, you stop. Okay, so then you have a score for each user, right? Then you divide the score. Then what they did, they then divided the score into 5 bins. Okay, and they say that the users whose belief score is between 0.75 to 1, they are known hateful, KH. And the belief score, users whose belief score is between 0 to 0.25, they are not hateful. Okay, and in this way they identify this many numbers. This many number of users are known hateful, this many numbers are non-hateful users. Okay, in order to, so they also proposed a new diffusion model. They call this model as LRIF, least recent influencer model, right? And this idea is again very simple. Now look at this retweet graph here. So the idea is that, and these are users, and these numbers indicate when these users, individual users posted a hate speech. Say B posted a hate speech at timestamp 100, C posted a hate speech timestamp 300, and so on, right? So what this LRIF model does, say look at C, right? Remember, this is repost network. That means C has posted a tweet which is either posted by B or either posted by, just a minute, either posted by B or either posted by A. Either posted by B or by A, because you see the connection here, right? Now, in case of least recent influencer model, basically we look at which one is the least one. 100 or 0. So 0 is least in this case. It means this model assumes that C is being influenced by A, not by B. Okay, so we remove this edge. Okay. Similarly, look at D. D has shared B's post. D has also shared E's post, but B has posted this earlier. So we only keep this edge, we remove this edge. This is called least recent influential model. Okay. So these are their takeaways. Let's not look into trying to understand these figures. But the takeaway is that the post of hateful users spread faster, wider, deeper, and more quicker in the initial stage. Right, the time taken for the known hateful cascades to reach a particular value is lower in the initial stage, implying that possibly that known hateful cascades are significantly faster initially, right? This can be attributed to the possibly high proportion of known hateful users present in the system, right? So the second paper, this was also very interesting paper. They looked at several social properties, social characteristics of hateful users. This is more about a kind of analysis, less modeling, more analysis kind of paper. Okay. So what they did is that first they collected data from Twitter, right? They collected around 100K users and around 2.2K retweet ages, right? Along with user history. For each user, they collected 200 most recent tweets, right? And then from this data set, they created a transition matrix. Okay, a kind of an adjacency matrix which indicates that whether you has retweeted these tweets or not, right? 0 and 1, or you can think of a weighted transition matrix. Okay, now how this model works? So this model starts, and they also identified a set of hateful lexicons. Okay, now how this model works? For each user I, okay, they first initialize a vector at timestamp 0, right? And this vector indicates whether the user has posted a hateful tweet, right, or whether the post written by the user has at least one hateful word or not. Okay, so think of a vector, okay, vector of size n, where n is the number of users, and the ith entry of this vector corresponds to the ith user, and it is 1 if that user has posted at least one hateful word in the past, otherwise 0. Okay, so now the same thing is happening. So you use the kind of a PageRank process. You update this p with the values of t, right? You multiply t by p. T is a matrix, remember t is a transition matrix, and p is the initial vector, right? You keep on updating this p value unless you see a convergence. Okay, so once the model converges, you have some hateful score for individual users. You again divide it into 4 buckets, the way the other paper did. Here also you divide into buckets, 4 buckets, 0 to 0.25, 0.25 to 0.50, and so on, right? And then you analyze the results. Here also again, due to time constraint, I'm not going into the details of these figures, but the takeaways are as follows. The takeaways are that hateful users tend to have newer accounts. Okay, hateful users tend to tweet more and in short intervals. Okay, their frequency velocity is high, tweeting velocity is high, and hateful users are more central toward the dense part of the network. Okay, so moving on, this is the last paper that I'm going to present, and this is our research. So we recently did a work to understand this hate speech diffusion in a different way. So unlike existing research, which mostly focus on internal signals, tweets, networks, and so on, we relied on additional signals coming from outside Twitter. So this is a first work which incorporates both internal signals, which we call uh, endogenous signals, and external signals, which we call exogenous signals, into the model, right? So the idea is very simple. The idea is that when a particular user retweets something or tweets something, he or she is possibly influenced by the internal signals coming from Twitter, which is endogenous signals, and the signals coming from outside Twitter, which is exogenous signals. So therefore, in order to measure the virality or spread of a particular tweet, you may need to rely on both the signals, internal signals as well as external signals. Okay. So we collected tweets. We collected tweets more than 161 million tweets and more than 41 million users, and we manually annotated 17,000 tweets. It took a lot of time. We also ran existing hate speech diffusion model like Davidson model to check whether and we also trained that model on our data set and tried to annotate other tweets into hate or not. So remember that here the task is not to come up with a hate speech detection model, but to come up with a hate speech propagation model, right? So then we solved two tasks. One is called hate generation task, other is called hate diffusion task, right? What is this hate generation task? Hate generation task basically says that given a tweet and a user, can we predict whether this user has tweeted this tweet or not? To understand, in order to understand whether user UI is a spreader or not. Okay, and in order to understand this, we took into account SEN. EN is the endogenous signals, basically users history. SEX is the exogenous signals coming from news articles. So we leveraged news article streams, right? And HID, sorry, SEN is the endogenous signals of other endogenous signals, other tweets of users. HIT is the history of user I. Okay, so we relied on the history, endogenous signals and exogenous signals, right? And these are the features that we used. So directly coming to the model. So we have two models. One predicts the retweeters of a particular tweet in a static environment, and another predicts the retweeters of a particular tweet in a dynamic environment. What do you mean by static and dynamic? In static environment, given a particular time, right? Say for example, we have history till t. We want to predict who are going to retweet next, right? Next in the sense like there is no time bound in the future sense, right? In case of dynamic retweet prediction, we basically ask that given a history till t, who are going to retweet within t plus delta t. So delta t is fixed. So in case of static retweet prediction, delta t is infinite. In case of dynamic retweet prediction, this is finite. Okay. And let's look at the model. So we call this model as retina. Okay. So what it does is that is xn, and you see that there are two embedding passing over the network. xt is the embedding of the tweet for which we want to predict the virality, okay, or the retweet, whatever, retweeter. And xn is the exogenous signal coming from the news articles. Okay, so here this is the simple attention model where these news articles are coming in, and this is attended by this tweets, right? And we get a kind of representation which captures both the tweet as well as a news article. Okay, this xtn is a joint representation, kind of a joint representation, you would say. Then this xui, u1, u2, these are the user history embedding, right? We are passing it through a deep layer, and we are predicting whether ui will be the retweeter or not. or UJ will be the retweeted or not. Static case. Dynamic case, same thing. Instead of having a feed forward network here, we replace it by a GRU, because this is a temporal modeling, right? And we also did a lot of tricks like upsampling, downsampling, selective feature selection, top K features, principal component analysis for feature selection, and so on, right? And it turned out that retina model with D, I mean, so D is the dynamic model, right? And this D this symbol indicates things after ablation. I mean, after feature selection. So we saw that it outperformed existing methods, including including statistical ML like regression descent tree, along with support vector and other classifiers. It also outperformed normal SIR kind of models, IC models, and so on. We also did a lot of other analysis to understand the importance of exogenous signals, the amount of information one should need as a part of user history, and so on, like, right? So here, as you see that, so this is the change in accuracy with the number of tweets, right? Here the change in accuracy with the number of history of that particular user. So you see that in case of history, with 100 tweets, with 10 tweets is same as 100 tweets. So history may not play an important role in general. So coming to the challenge, right? So we have seen models for spreading. We have seen models for epidemic modeling, information diffusion, so in particularly for hate speech and so on. Most of the works are focusing on influence analysis. There is less work on actual cascade prediction, in the sense like what is going to be the tree structure through which a particular news propagates. There is no work as such, and a very few work on theoretical aspect of these models, particularly in social network diffusion. Mostly people use some sort of neural models to show how it mimics the existing, mimics the real world behavior. Scalability is a very important issue. Most of the models are not scalable, and if your model is not scalable, that may not be useful for practical purposes, right? It is also, there are less models which are domain agnostic, platform agnostic. Say, for example, you have a model on Twitter, you can't use it for Facebook, or you can't use it for, say, Reddit, right? So platform agnostic model might also be needed in this case. In this case, closed world assumption is possibly a terrible assumption. So therefore, in our case, we incorporated this exogenous signals, but more research will be needed to explore this open world assumption, right? So whatever I discussed are mentioned here in this list of references. That's all. If we have any question, we'll be happy to respond.
Thanks, Dr.
Thanks for your
Tanmoy,
questions.
for this excellent talk. If anybody has any question, they may ask directly.
Okay, so this is just the last slide. Would like to thank all my collaborators, all my funding agencies for supporting us, particularly in the research related to hate speech and fake news, right? I'm not sure if some of the potential PhD seekers or like researchers planning to do hard studies are present here in this audience panel, but this is just for the information that we are recruiting students, including RAs, PhDs, and postdocs. So if you find our work interesting or relevant, feel free to contact us, and whatever course and data sets, everything we developed over time, This is already available in this GitHub link. So please feel free to go to the link to get more information. Thank you very much for your patience.
Okay, Dr. Tanmoy,
Thanks. Thank you.
thanks for your excellent talk. And from the organizing committee, I'd like to thank all of the participants for being here. Thank you.
Thank you
With
very
this,
much.
we are ending this session. Thank you all.